Hey folks, welcome back. Today we are going to start Chapter 5 of Physics 11, which is looking at forces, dynamics. We're going to spend some time in this chapter talking about why things move. We've already talked about how things move. We've done lots of calculating of accelerations and final velocities and initial velocities and displacements, but we never actually talked about what would make an object actually accelerate or move in the first place. So that's going to be this chapter. This chapter is very, very important. I would say of all the chapters, of all the information we look at in Physics 11, this is the chapter, the bread and butter of physics. If I had something like 10 classes to teach you guys physics and that was it, I would pick just this chapter. So this is really, really important. This chapter, you'll find some of the stuff is a little bit tricky. It might take some time to wrap your head around it. So practice is going to be really, really important, and joining in on the Zoom meetings to ask questions about practice questions and homework will also be really important. So hopefully you can join me and your classmates for that. But let's dive into some dynamics. I already mentioned it's all about forces. A force is really just a push or a pull. Sometimes it could be a force you can see, like a person physically pushing or pulling another object. But other times it could be forces that exist that we actually can't see, but we know they're there. Things like gravity or friction. Forces are vectors, so they have a size or a magnitude, and direction is also important. And the units, you've probably heard of this fellow, named after a very famous physicist, Sir Isaac Newton. Something as the story goes, what was it? He's sitting in an orchard and he got plunked in the head by an apple. And determined that there must be some force, which we now call gravity, that pulls all objects downwards towards the earth. Sounds like he actually wasn't hit in the head, but he was walking through an orchard and saw all of the apples on the ground and thought that, hey, everything does come down. And he was the first one to start thinking about forces and gravity in particular. There are only four main forces. You probably don't have to write this little note down. But just to give you an idea about some of the sort of big umbrellas that cover the different forces in this universe, there's gravity, which we're going to look at today as the attraction between any two masses. Electromagnetic forces exist between charged particles or magnets. Friction actually fits in there. We'll look at that in the next lesson. And then we won't have time for 3 and 4, but weak nuclear forces are what cause radioactive decay. So alpha, beta, and gamma decay. And strong nuclear forces are what hold a nucleus together, which has a bunch of protons in close proximity, and that shouldn't really happen. Those positive charges should actually repel, but it turns out the strong nuclear force holds them all together. But here's what we want to chat about for this lesson, gravitational force. We usually think about gravity as being a characteristic of planets, of things that are really big. But actually gravity exists between any two masses. So you're sitting in front of a computer potentially right now. There is a gravitational force between you and your computer, and you and your phone, and you and your family members, and you and your car. There are attractions, these pulls between any two objects that have mass. So in a little picture, there's the two objects. You can see we're going to have all these forces. We use a capital F and a lowercase g in this case for gravity. We'll see lots of little subscripts, F for friction and E for elastics. That's coming down the pipe. But for now, we've got F with a little g for the force of gravity. Those two masses are going to pull on each other, and r is the distance between the two masses. And based on that little picture, we have an equation that Sir Isaac Newton came up with. It's called the universal law of gravity. It's universal because it's not Earth-specific. This equation actually would work on Mars or the Moon or anywhere that you want to go. And that equation is what I will call big G, because we will actually see a lowercase g in addition to the one sitting right here. But it's big G multiplied by the two masses divided by r squared. M1 and M2 are your masses in kilograms. R is the distance separating the centers of the two objects. That needs to be measured in meters. It's quite common to see it sometimes in centimeters. So do watch your units when you're doing the practice questions. And big G is a constant. Don't sweat the units. The units are what they have to be to just give us newtons in the end of this equation. but the number is 6.67 times 10 to the negative 11. So those of you with graphing calculators, I want to show you something cool. You can actually store that number as the letter G in your calculator. So if you've got a graphing calculator and you type in 6.67 EE negative 11 and then hit the store button, which I'm circling right now, it's right above on. You'll see a little arrow shows up, and then you want the letter G. So to get that, you hit alpha tan or alpha G, hit enter, and it should spit that number back out at you. That number is now locked in as the letter G. So when you go to type in an equation, you don't have to type the number as 6.67 second function E negative 11. You can actually just hit alpha G. And your calculator now knows that that letter, when you type it in, is worth that value. Pretty slick. It'll save you a little bit of time here and there. We're going to skip this and come back to it. There we go. Here's what I want to try right now. Let's try a really easy equation to find the force of gravity between a couple of people. Mass is 45 and 68 kilograms if they're standing 2.1 meters apart. So you go to that universal law of gravity equation. You plug in big G, you plug in the two masses, divide by the distance between them squared. Don't forget to square that. And your calculator should spit out 4.6 times 10 to the negative 8 newtons. Now, when you're standing beside somebody else, you can't feel that attractive force. It turns out that 1 Newton is about the amount of force it would take to push one of the keys on your keyboard if you're going to type something on your computer. Just to give you an idea, or maybe the amount of force that your thumb is exerting on your screen when you send a text message on your phone. So here at 4.6 times 10 to the negative 8, you're definitely not going to feel that attraction between you and another person, which is actually probably a good thing, because you can imagine that life on this planet would be very strange if we actually did feel these little tugs and pulls between people, or between myself running down the street in a dump truck. That would be bad if there was a gravitational force big enough that we actually stuck to each other. One other thing I should mention, let me scroll back a little bit, is when you're using this universal law of gravity equation, sorry about that little hiccup, my kids are fighting, joy. When you're using this universal law of gravity equation, you will see that both of the objects pull on each other. That FG that I've labeled in this diagram is actually the same value. So we don't have to find a separate force of gravity of 1 pulling on 2 and then another one for 2 pulling on 1. The cool thing is, in this equation, when you solve for the force of gravity, it is just the 2 objects pulling on each other. So let's try a second example here. Sometimes we'll use that universal law of gravity, but you won't be asked to find the force of gravity. You might be asked to find one of the other variables in the question. So here we're looking for the distance separating a couple of masses, and they're giving us the force of gravity. So in this case, we're looking for r, which means we actually have to solve for r squared first. In this case, the algebra, you would multiply both sides by r squared, and then divide by 6.2 times 10 to the negative 13. So the r squared and that FG kind of just do a little switcheroo. Plug that into your calculator. Don't forget to take the square root. You'd end up with 46 meters separating those 2 masses. Third example. What's the force of gravity on a person who's standing on the earth? So I want you to think about that for a little bit. If we're going to use that equation, Fg equals big G m1 m2 over r squared, what kind of values might you need? And hopefully there's a few of you going, well, the 80 kilograms, that's going to be one of the masses, but the Earth is the other one. So you'll need the mass of the Earth. And then how far apart would that person be from the center of the Earth? Well, that would be the radius of the Earth. So here's the 2 values you're going to want. Both of these values are on the formula sheet, so you don't need to memorize them. You could store them in your calculator if you wanted to. Now you know how to store numbers as letters. But you could always go look those numbers up. So in this equation, big G times the mass of the Earth times the mass of the person divided by, don't forget to square the radius of the Earth. Sometimes when r is a big value, like it is in this case, 6.38 million meters, sometimes people see the scientific notation and then forget to square the number. But you do need to square it. And you go and you type all that into your calculator, and it should spit out 784 newtons. Now, that calculation is not hard, but in physics, we quite often like to find the force of gravity for objects on the surface of the Earth. And it's a little bit time-consuming to have to refer to your formula sheet every single time to go and find the radius of the Earth and to find the mass of the Earth. So what I want to show you is a little shortcut for all objects. We're going to call it mass number 2 if they're sitting on the surface of the Earth. So in that equation, the universal law of gravity, I'm going to get you to try something out here. So here's the equation. And what I want to do is see if we can figure this out. What if we did this part of the question right here? So we're going to leave M2 for a minute. What if we just typed in big G and we said, hey, mass number 1, let's plug in the mass of the Earth. And for r squared, hey, for an r value, let's plug in the radius of the Earth. Sorry, I don't know why one's capitalized and one isn't. Why don't we figure out what that number is equal to, the stuff in the red circle, and then we can just turn it into a single number, and then we could just take that single number and multiply by mass number 2, whatever the mass of the object is. And if you go and you plug that into your calculator, give this a try. I'm just going to type it in as big G times 598 times 10 to the 24, all divided by the radius of the Earth, 638 times 10 to the 6, all squared. And we're going to have that number multiplied by M2. So I want you to try typing in the stuff that's in blue there. And again, humor me and actually try it on your calculator. You're going to get a number where hopefully you look at it and you go, oh, I should have seen that coming. It turns out if you type all of that into your calculator, you're going to get a number that you've seen before. And that number is 9.8. Now in this case, it actually turns out that the 9.8 isn't meters per second squared. It's got units of newtons per kilogram. But the equation ends up looking like that. On your formula sheet, we don't actually write it as 9.8 times M2. We actually do this. We call it the force of gravity equals, we just change up the order. We put the other mass first, and then we put a little g as opposed to a capital G. So in this case, that's the equation for all objects sitting on the surface of the Earth. It's a great little shortcut. And in this case, that little g is something called the gravitational field strength. Gravitational field strength. So quite often people will say, oh, what's gravity on Earth? And they go, oh, it's 9.8. It's actually that the correct term should be what's the gravitational field strength on Earth. And that value on this planet, at sea level anyways, little g is equal to 9.8 newtons per kilogram. Now that gravitational field strength, that value of 9.8 is specific to this planet. If you go up to the moon, it's quite a bit smaller. And if you go up to like Jupiter, a bigger planet, it's actually quite a bit larger. The homework that goes with this lesson is going to be something called Worksheet 1. And there is a question on that worksheet where you're going to calculate the gravitational field strength using this little shortcut, but plugging in the information for a bunch of other planets. And it's kind of cool. You can do a little thought comparison between Earth and other planets. Like the moon, for example, the gravitational field strength is about 1/6 of what it is on this planet. So that means if you went up to the moon and you tried to play basketball, you would shoot a basketball, and if you shot it with this sort of same amount of like muscle force, the ball would go 6 times higher. It would travel 6 times further. It would be in the air for 6 times longer. In fact, if you wanted it to feel like basketball on this planet, you'd actually need to make the hoop like 6 times taller. So you'd actually want to be playing on like 60-foot tall basketball hoops just to have it feel the same. Very, very strange. But again, kind of a cool little thought process or thought experiment. We'll call it a curse of the physicist moment. So there's a great shortcut for all objects on the Earth. Just take the mass. Like, hey, what's the force of gravity on my cup of coffee? Well, I could just measure the mass in kilograms and multiply by 9.8, and it would tell me how many newtons of gravitational force are acting on that coffee cup. So a great little shortcut where I don't need the mass of the planet or the radius of the planet anymore. Scroll through that. Here's a bit of vocab that I'm not going to test you on, but it is something good to know as a physicist. When you go and you calculate the force of gravity on an object, like we just did for that person, who was, 784 newtons? That is actually the person's weight. And we flip-flop these two words, this mass versus weight. In everyday speak, people get them wrong all the time. But mass is, in a physics sense, it is technically just how much stuff an object is made out of. It's measured in kilograms. And weight is then the force of gravity acting on that stuff. So that means if you go up to the moon, your mass is unchanged. You are just like 80 kilograms worth of stuff. It doesn't matter where you go. If you've got a mass of 80 kilograms on this planet, you've got a mass of 80 kilograms on every other planet, assuming you haven't lopped off an arm or a leg or something. But if you go to different planets, because that gravitational field strength is different, then your weight would be different. So the person in our example that was 80 kilograms of mass had a weight of 784 newtons, but on the moon it would only be about 131 newtons. So if you say, hey, how much do you weigh? And somebody says, oh, I weigh 70 kilograms. That's actually not right. You've probably never calculated your weight before, right? Your mass in kilograms times 9.8, and it spits out a number in newtons. You could try it out if you want. I'll do mine. What am I, about 72 kilograms times 9.8. So the force of gravity acting on me, also known as the weight of Mr. Heinrich, I'm about 706 newtons. You don't measure pounds, you don't measure kilograms. Weight is measured in newtons. And one other thing to show you with this lesson, another kind of cool little shortcut, is something called the inverse square law. So I want to show you a special type of question where we can use a little trick. And this trick works great because the distance separating the two objects, r, is in the denominator of our equation, and it's squared. So if I give you some information, we have two unknown masses. We don't know what they are, but I'm telling you when they're 12 meters apart that the force of gravity, aka the force of attraction between them, is 400 newtons. That's sort of what I'm going to give you. And now I might ask you, what happens to the force of attraction if we shrink the distance down and we make them only 4 meters apart? And this is a question where a lot of times students will look and they'll go, okay, I might know the trick here. They were 12 meters apart and now they're only 4 meters apart. They actually just got 3 times closer to each other. And people will sort of look at that and they'll go, well, when objects get closer, you're dividing by a smaller number, so the force of gravity should go up. So the force of gravity will increase. And they say, well, 3 times closer, that means the force of gravity increases by a factor of 3 as well. So shouldn't the force of gravity get 3 times bigger? And the answer is not quite, but you're close. If we make these objects 3 times closer, because we're squaring that difference in our equation, here we're not actually increasing the force of gravity only by a factor of 3. We actually increase the force of gravity by a factor of 3 squared. So the trick with these questions is figure out how many times closer you've made the object, or it could be further away. Figure out how many times closer or further away it's become, and square that number. So in this case, 3 times closer actually means the force of attraction is 3 squared, it's 9 times bigger. And if it was 400 newtons and we're 9 times bigger, you can simply multiply the 400 by 9, and you've got a new force of attraction of 3,600 newtons. So let's try one that's, I guess, the opposite. We're going to go back and say, hey, if it's 400 newtons when they're 12 meters apart, what does it look like if we stretch the two objects and we pull them further apart? We actually make the distance between them 60 meters. Well, you can look at that and you can say we're 5 times further apart. That means the force of attraction goes down. There's less attraction when you get further away from the planet. The same for any two objects. Here you're 5 times further apart. That doesn't mean that the force of gravity got 5 times smaller. It got 5 squared times smaller. So in order to actually calculate the number, it was 400 newtons. Now we're looking for something 25 times smaller. So you simply divide by 25 and you'd end up with 16 newtons. So a great little trick. It's called the inverse square law. You'll see questions like that on worksheet 1, today's homework. I'll bring that up in just a moment. And it's a cool little trick where you just figure out how many times closer or further away the objects have become, square that number, and then you can head to your calculator to get your final answer. So here's the worksheet that goes with this lesson, Chapter 5, Worksheet 1. It's all about the force of gravity. Give this a try. Don't forget, I do have in the All Resources folder, that's where I found this worksheet. You also have the chapter outline and the answers to all of these worksheets and homework questions, or full solutions on the website as well. So give this a try. There are, holy slow computer. What have we got? 7 questions for you to try. You'll notice questions 8 and 9 have little stars. Those are optional questions, kind of above and beyond what you're expected to know, but kind of fun to try if you've got the time or the energy. So give that practice a go and join me in one of the Zoom meetings if you have any questions about anything from this lesson or from this worksheet. We'll chat with you soon.